So we've been talking about derivatives, a function having differentiation at a particular value. We've been looking at the formal definition of a derivative to help us find the derivative at a particular point or of a function. And we talked about that that is telling us basically what is happening at a particular point on a function. What is that rate of change happening right there? And so basically we're talking about the slope at particular points on a function. And so we also looked at the slope of a tangent line. And this is going to help us because we're going to get into graphing derivatives given the function, the graph of a function. And so here we're trying to find what is this slope right here of this tangent line or at this function at this point 213. And so because they gave us the tangent line here, basically all we need is 2 points on the line. We're given one of them. We're given that we have the point 213, and then we can find another point on this line. So I'm just going to choose one where it looks like it's crossing. So maybe right here. And so this is when our x value is 3. Our y value then is 15. And so given 2 points on a line, we can find the rate of change. So it's the change in our y value, which is 15 minus 13, all over the change in our x value, which is 3 minus 2. So this gives me 15 minus 13 is 2, all over 3 minus 2, which is 1. So our slope here, when x is 2, has a slope of 2. Okay. So notice that our slope is positive, and notice that as we're looking at this graph, this is increasing at this value. So let me just kind of extend this a little bit further. So we know then if this was our graph of f of x, oops, sorry, if this was f of x, then we know that f prime of 2, in our case, the derivative of this function at 2 is 2. And so we actually have a point on that graph of the derivative. Notice if you had chosen a point down here, maybe when x is 1. If I looked at this slope of the tangent line, I'm just going to estimate it. Notice this slope here is going to be larger than our slope here. That line is steeper than the red line that we just originally took it. And if I look at this, I can look at what my y value is. So that's about 8. So when x is 1, our y value is 8. And then I can choose another point on this line. I don't know. How about when x is 0? It looks like we have about 4. And so if we looked at the slope between these 2 points, so 8 minus 4, change of a y value, 1 minus 0, this gives me 4 over 1, which is 4. So if we looked at the derivative of this function f of x, f prime of 1 is 4. And I could tell by on my graph, again, that this slope was a larger slope. I should get a larger number than this one. So notice if our slopes are positive, then on our function, then our graph, notice of our derivative, our slope is positive, and where our y value is going to become back positive. So that means I have to be above the x-axis. So these are things that can be helpful when we're looking at a graph of a function and then trying to graph the derivative. And so let's look at this. So if f prime of x is greater than 0, we know the graph of f of x is increasing. and the graph of f prime of x will be above the x-axis. So let me grab this and bring it down. So if our graph is decreasing, come on. Doesn't like that, okay. I'm just gonna go over here. So if our derivative is less than 0, that's telling me my slope at a point on my graph f of x is, the graph is going to be decreasing. So the graph of f of x is decreasing, and the graph of the derivative f prime of x is below the x-axis. And then another one that's really helpful is when you find that our derivative is 0. Well, when your derivative is 0, that's telling you that the slope is 0, and the slope is 0 of a horizontal line. And so if you find that your derivative is equal 0, then the graph of f of x could, might not, have a max or min point, or the graph of f of x could be constant there. Which means a horizontal line. So for our point on the graph of our derivative function, or what our graph of our derivative function would look like if our derivative was equal to 0, it's going to cross or touch the x-axis there. Okay, so the graph of f of x, or the graph of f of x touches or crosses the x-axis. And then we got to be careful about what places where our function is not differentiable. And so there was different areas where our function wasn't differentiable. It was where it was undefined. You could have a jump in your graph, or it could have a sharp corner, or we talked about it having a vertical. The slope would be undefined there. So if f of x is not differentiable, at a point Then f of x either has a sharp corner there, it's discontinuous, so we saw things were discontinuous when there was a jump in the graph or there was a vertical asymptote. Oops, I don't know what I just hit. Sorry. Okay, so if that happens, then we're going to have in our graph of f prime of x, we're going to have an open circle. So graph of f prime of x will be undefined here. And you need to put an open circle. On the graph of f prime of x. Okay, so these are just kind of ways to help us get a picture of what our derivative function would look like given the graph of f of x. So we're kind of looking at a couple things. We're looking at where is our graph increasing, and where it's increasing, we know that that graph of the derivative function is going to be above the x-axis. We're going to look at when is our graph decreasing, our function, and we know when we're graphing the derivative function, at least that piece has to be below the x-axis. We're going to look at when our graph has max or mins, so peaks or valleys of our graphs, or where it's constant, it has a horizontal line in our graph of f of x. That's where the graph is either going to be touching or crossing that x-axis. And then we need to look at, is it differentiable at any values? Okay. And from there, we can start putting things together and getting a graph of what the derivative function would look like. And so basically, the point on our original function, we had x comma f of x. So f of x, remember, is just another way of writing y in function notation. So for our derivative, the point on our derivative function, you're going to have the same x value you had on your original function, but the y value is going to be the derivative at that point of the original function. So maybe we can take that one example that we just had. I'm wondering if I could actually copy it. I did. And see if we can graph the derivative function of this first piece. Let me just blow it up. Okay, so let's just kind of again talk about a couple of things we know. So we know our point, which was at 213. This was on f of x. And when we graph f prime of x, it's going to have the same x value, which is 2. And we found the slope here. What did we find that slope to be? Was that 2? Yeah. We found that slope to be 2. And then here we looked at when x was 1. When x was 1, we said that our y value was 8. And when we took the derivative, or we found that slope with the tangent line there, we found that it was 4. If we look at this, notice that in general, our graph of f of x it increases for all the x values until it looks like we hit 2.5, right? So this graph is a parabola. It's increasing, increasing, and increasing until we get to the x value of 2.5. So from negative infinity to 2.5. So I know f prime of x is above the x-axis. For those values, negative infinity until we hit 2.5. We even have a couple other things, right? We said we have a point at 2, 2. We have a point at 1, 4. And then here, let's see what's happening at 2.5. On our parabola, our y value, well, it can't be 13 because this was 13. So let's say that was 14. So x value is the same, 2.5, but our slope at a maximum point, the equation of our tangent line, that slope is 0. And so our slope here is 0. So we know that we're hitting the x-axis right here at 2.50. Now, if we look at the graph where it's decreasing, so at 2.5, it's going to change direction and it's starting to go downhill forever. And so the graph decreases It's decreasing when we're doing interval notation. So it's starting at the x value of 2.5. And then it's going forever. So to infinity. And so we know then f prime of x has to be below the x-axis here. So we can kind of do the exact same thing we did before. We can find a couple of points on this. So find a point on this graph. So maybe when x is 4. Although we know that this is actually kind of symmetrical, right? If you drew a vertical line at x equals 2.5 and you folded this paper, wouldn't it be asymmetrical? So this point right here that was at 213, it should fall right here at 313. So I know I have a point at 313 on f of x. And we knew that that slope here, well, this was positive 2. What do you think it's on this side? So that should also be symmetrical, except that it's decreasing. So we can kind of get an idea that, well, then we know that at 313, if I'm looking at my derivative function, that would have to be, slope is negative because it's decreasing. So at 313, I have 3, negative 2. It's about right here. And then we said that at 1, so if I did, that's 1.5 over in this direction. So I have to go 1.5 over in this direction, which would hit me at 4. That 4 value, I did that over here. So at 4, we have 8. But our slope is going to be negative 4. So I don't know if you can see what type of graph we're going to get. But if I graph these now and put it together, so the graph of the derivative function from the parabola function is a linear equation or a linear line. Okay. Let me just pause. So this activity, or what we're doing now, is just really giving us a good kind of idea of what we're doing when we're taking a derivative at a function at a particular point. And basically, again, we're just looking at the slope of what's going on that function at that point. And when you don't have a line, then we can't just tell us what the rate of change is at that point. Okay, so I'm not going to do that second one from that in-class exercise. So I'll let you guys work on that later. If you didn't do it, maybe you can now find the slope between, or the slope of the tangent line at that 0.34. Let me see if I can find that one graph that I kind of threw off. It wasn't being nice. There it is. Let me put it down here. Yeah, that's not the one I wanted. Okay, so here we have the graph of 4 graphs, and we have the derivative function and the original function. So the ones on the bottom, 27, 28, 29, and 30, those are the original function. And from there, you should be able to determine what the derivative function would look like. So looking at number 27, notice that it's decreasing everywhere. It's decreasing everywhere until we hit x equals 0. And so we know from this value then, this piece from negative infinity to 0, this is decreasing, m is less than 0. So the graph of f prime of x falls below the x-axis. Okay, well, a lot of this you could really do trial and error, just checking it. If I looked at this first graph up here of the derivative function from 0 or negative infinity to 0, this function is not below the x-axis. This is above the x-axis. So that couldn't be it. This piece here from negative infinity to 0, my graph is below the x-axis, so that's a possibility. So let's come back to it. This one here, the graph from negative infinity to 0 is not all below the x-axis because of this piece in here. So this can't be it. And same reason with graph D. And so the only one that would fit here would be this graph B. And let's just make sure. So where it's increasing, where it's going up from left to right, this graph of the derivative has to be above the x-axis. So from 0 to infinity, m is greater than 0, f prime of x is above the x-axis. So it's above the x-axis here from 0 to infinity. So this would match graph B. The other thing was, remember, a max or a min was where it was going to cross the x-axis, and it was the same value right here. Okay, so if we jump to number 28, please don't do that. Notice that this graph 28, it's pretty much strictly increasing everywhere, right? So we're increasing, 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 increasing. We might level out a little bit. And then we're increasing, increasing, increasing. So for this graph, f prime of x, and our graph is always greater than or equal to 0. So it's going to be above or touching the x-axis everywhere. So only thing in my scenario that looks like that would be graph A. This is all above the x-axis, touches the x-axis, and then above the x-axis. And so 28 would have to go with A. So in a way, we're kind of cheating because we have those graphs to look at and kind of see, do they match right with what it's talking about? So this one right here, notice you have a lot of max and mins. So these would be all values where our slope is 0. The values where f prime of x equals 0. So notice that we're going to have multiple places where it's going to cross the x-axis. We're going to have one about here. We're going to have one about here. So there's 1, 2, at the origin, 3, 4, 5 spots where it's going to cross the x-axis. And so notice here, 1, 2, 3, 4, and 5. So they're the same x values. Where we have max or mins is where it's going to cross the x-axis for our derivative function. And so here on the left of our first one, notice it was increasing, so this was above the x-axis. Anything that was increasing, so increasing, was above the x-axis. And everything where it was decreasing these were values where it had to be below the x-axis. And so this one is with graph D. And last but not least, but let's just go and make sure and show why it works. So this is decreasing. And then we have a horizontal, we have a max, so it's going to be a horizontal slope here, which means it's going to be an x-intercept. So x-intercept. This was decreasing until we hit that x-intercept. So it had to be below the x-axis. And then here it's increasing. So it's going to be above the x-axis. Here at the origin, the slope, we have a max. So the slope is 0. We're crossing the x-axis. It's decreasing until we hit that min. So it's below the x-axis. So at the min, it's where it's crossing. And then it's increasing forever then. So it's above the x-axis forever then. And so this graph here relates to, what did we just say? C. Okay, so we took graph of the original function and we were able to go through and find the derivative function. So let's see if we can pull one more, and then I really don't want to spend too much time on this section. The next section is going to be it's going to hopefully make your life a lot easier from now on for taking derivatives. But hold on for a sec, let me pull one question. Okay, so I pulled an example from the book, and so if you ever wanted to go back and refer to it, it's on page 197, number 11, and we're given the function of f of x, and we're asked to graph f prime of x. And so a couple things, again, that would help us is seeing where it's decreasing, where it's increasing, maybe max or mins, and discontinuity, or where it's not differentiable. Okay, so decreasing, I notice this first piece right here is decreasing until we hit x equals -2. So basically, from -infinity to x equals -2, our graph will be below the x-axis. So f prime of x is below the x-axis. Notice though that the slope, any point that you choose, if I chose it at x equals -4, my slope is the same here as it would be at x equals -5 or x equals -3. All of these have the same slope because it's a line. And so we could find the slope. So we can do that. So let's do that. So we need 2 points. Let me just erase that so I can see better. Okay, so it looks like -3. We have a point at 1. And at -4, we have a value at 2. So if I look at rise over run, the change in my y value, so 2 minus 1 all over -4 minus -3, which is 1 over -4 plus 3 is -1, which makes sense, right? We fall 1, we go over 1. We fall 1, we go over 1. So we know that our y value, basically, the y value of the graph f prime of x is equal to -1 for x contained in the interval from -infinity to -2. Okay, so we can actually graph that real quick. Okay, so at -2, we have a y value, make it bigger, of -1. I'm going to put an open circle at that point, -2, -1, but that's a horizontal line. Okay, so that was just for that piece. Maybe we can jump and let's look at the piece from 2 to infinity for a minute, because I think that's going to be an easier piece also. So we look at this piece, x equals 2 going all the way up to infinity. We know here from 2 to infinity, our graph is increasing. It's going upwards. So we know that f prime of x is above the x-axis here. We're also given that this is a straight line. And so we can find the slope. So choose 2 points on this line. So how about x equals 2 and x equals 3, 2. So we have one at 2, 0. And we had one at 3, 2. I can plug in the formula, or I can say, oh, I look like I'm rising 2, running over 1. So 0 minus 2 all over 3. Sorry, and minus, 0 minus 2 all over 2 minus 3. I knew something was wrong. So I get -2 all over -1, which was 2. So we know that our graph then so the y value of f prime of x is equal to 2 for all x values that are between 2 and infinity. So that funky kind of E looking is saying it's contained in, it's a value in that set. And these numbers, this is a set of all your x values. So from 2, so 1, 2, we had x value 2. So an open circle and then a horizontal line. Okay, so the last piece is that we have to graph this middle. So between -2 and 2. We'll notice that it's increasing. It levels out so that our slope is 0, and then it's increasing. So to me, this is telling me that it's all above the x-axis, except it's touching because it's giving me a horizontal slope here. So I know f prime is 0 there. So this is where it's going to touch the axes. Basically, we have an open circle. We're going to come down. We're going to hit this. We're above the x-axis. And then we're going to have an open circle. And we're going to come back up and hit it. So our slope here is steeper, and then it's leveling out. So that's what the graph of our derivative function would look like. Okay, so let's stop there and take a break. And this was the last bit of chapter 3. So I'm just going to stop the video and start a new video after break for the new information.